Welcome. This is the lecture for kinetic energy, potential energy, and the conservation of energy. Imagine you are at the amusement park, preparing to ride the monster roller coaster. Slowly the car rises to the highest loop in the park. You stare down the abyss on the other side. Where does the energy come from? How does the car remain in motion? Why does it speed up on the other side of the next hill? We will explore how energy is conserved and remains in bodies in motion and in stored potential forms. You have reached the top of your roller coaster ride and you begin down the other side into the exploration of physics of potential and kinetic energy. Kinetic energy is the energy of motion. An object that is moving has energy within it. We can quantify that energy using the formula 1/2 mass times velocity squared. Our new units for energy are joules. There are all forms of energy, but we will look at specifically kinetic as in relation to potential energy. As we go from movement to stopped, we will store the energy of motion into a potential energy bank. This section is an exploration of how we account for energy. We are to become the accountants of all energy, because energy cannot be created or destroyed. It simply changes forms. In our first example problem, which we will work together in class, an 870 kilogram compact car speeds up from 22 to 44 meters per second while passing another car. What were its initial and final energies, and how much work was done on the car to increase the speed? Conceptually, it's important to understand that the car must receive energy to increase its speed by quantifying the amount of energy in the first speed and mass of the car in relation to the second speed and mass of the car. We can tell how much energy was added to this system to increase the speed. These are the types of problems we will see as we work with kinetic energy and mass. The next form of problem that we will see is problems of potential energy, denoted by the variable U. This is stored energy, energy that can be expressed as kinetic energy or other forms. Our exploration will focus on kinetic. Many times we will look at how energy is stored gravitationally. If we move an object higher against gravity's force, we will store more energy in the object relative to its position above the Earth's surface. The other form that we may explore is elastic potential energy. It is stored in objects that are stretched or spring-loaded, such as a spring, a bow, or even strings on a musical instrument. All of these objects can be manipulated to store and release energy. the energy that is stored within them as potential can be expressed into kinetic, sound, or other forms of energy. To discover how much potential gravitational energy we have, we will use the expression U sub G equals mgh. This refers to the object's mass times the gravitational constant times the height that the object has been moved from its reference point. The potential energy of gravitation is explored in an example problem. As you lift a 2-kilogram textbook from the floor to a shelf 2.10 meters above the floor, what is the book's gravitational potential energy relative to the floor? And what is its gravitational potential energy relative to your head, assuming you are 1.65 meters tall? Simply put, the mass of the object moved against gravity stores energy. The higher you move the object, the greater the storage of that energy. As the object returns to its reference point, or the ground in this case, it will express that energy often as kinetic energy. It is falling. The falling object has motion. So all of the stored energy becomes kinetic. That is how we lead into the understanding of the law of conservation of energy. The energy that is stored, for instance, in an object that is raised up against gravitation, must retain that energy, and it can be expressed as kinetic energy. Simply put, the total amount of energy in the universe is constant. In other words, energy cannot be created or destroyed. It only changes forms. The path an object follows in reaching the ground does not affect the final kinetic energy. See the figure in page 259 of your text. In figure 11.9, you will see a ball on an inclined plane. If the ball were to fall, free fall, off the side of the plane, it would have the same energy when it impacted the ground as if it had rolled down the other side of the inclined plane. Both times, if it had reached the bottom or fallen off the side, it would have the same amount of energy as it moved. The route that an object takes to return to its lowest point will always have the same kinetic energy, so the route is not important. Take, for instance, a pendulum. Work done on an object is equivalent to the potential energy gained, delta K. In the example illustration, the pendulum has the same potential energy at location A and D. This is the extreme of the motion of the pendulum. From this point, it will only return back through the arc. At point C, the pendulum has only kinetic energy, for it has gone to the lowest point of its swing. At point B, there is a mix between some potential energy and mostly kinetic energy. As we made the analogy earlier, you will be an accountant and sum up all the forms of energy that are present in a system. In this case, we see that at point B, the kinetic energy is 2 joules. At point A, we knew that the potential was 2.4. So the balance of energy at point B must be in the form of potential at 0.4 joules. When we reach point C, all of the potential energy, 2.4 joules, has been converted to kinetic energy. And at point D, it has returned to the potential energy once more. The pendulum is a very apt example of the transfer of potential and kinetic energy. If you focus, as we have discussed in class, on this system, you will be able to conceive of all the elements involved in potential and kinetic energy. You can account for the height difference between C and D to quantify the increase in gravitational potential energy. The mass of the bob raised from the location of C to the location of D will tell you exactly how much kinetic energy the bob has at point C. This is the challenge of this section, to equate potential and kinetic energy as we check our formulas and solve for unknowns. We must realize that always the system retains the total amount of energy. Again, I will refer to the accounting principle or analogy, the analogy of accounting. If you would like to think of it as total money that you might have in, for instance, a bank, no matter where you move the money in the bank, it is always the same. You have a way to account for all the money in this analogy, much like you have a way to account for all the energy in any system that we explore in physics. So, conservation of energy, as it is a mechanical energy, we have just explored the pendulum. This is a mechanical system, and it maintains mechanical energy as it moves from kinetic to potential. It is the sum of all forms of energy in a system. The mechanical energy that this is referring to can be explained by the pendulum as it moves between its extremes. If one form decreases, the other increases by the same amounts, since it is converted to that other form. This can also be explained as changes in temperature due to friction, but we will restrict our inquiry to forces that are conserved. We will not introduce at this time non-conserved energy forces. So we can say that total energy, E, is equal to the kinetic energy plus the potential gravitational energy, U sub G. Conservation of mechanical energy is said to be kinetic before plus potential of gravity before equals kinetic after plus gravitational after. Imagine